Okay, so now we're talking about section 5 in chapter 3, and then we're going to jump to section 6.7 on L'Hopital's rule. So L'Hopital's rule is just how to take a special trick for making all the limits problems that we've tried to figure out a lot easier. And so we're going to start with section 3.5 on curve sketching. And the best way to do that is just to start with an example. I think example 1. Do that, I'm just copying it along, but I do it a little bit differently than they do. Process has a 5 or 6 point process. Oh, 7 points. I have 2 things I pay attention to, just the first derivative and the second derivative. 0 where it's positive, where it's negative. So here's the problem. 3x cubed minus 10x squared plus x plus 5. Okay, so we want to sketch this function. And the idea is, well, let's just analyze its first derivative and its second derivative. So we take the first derivative, 3 times 3, 9x squared minus 10 times 2 is 20x first power plus 7. And we take its second derivative. Uh, 18x minus 20. Okay, now what I care about is just finding out where the function is increasing, where it's decreasing, where it's concave up, and where it's concave down. If you sketch the graph of that function and you get the increasing, decreasing, concave up, concave down piece is correct, I'm happy. It's as good as you do by hand. And so all we're going to do then is just write out these lines, which are, this is going to be where f prime is positive or negative. And then I'm going to look for where f double prime is positive or negative on another number line. And so we just have to figure out where these things are positive or negative. And so, well, we set them equal to 0, same as before. Set them equal to 0 and solve to find where they're equal to 0. And that'll tell us where the and switch from positive to negative or negative to positive. Okay, so this first one, 18x minus 20 equals 0 is easy. It's just x equals 20 divided by 18. So x equals 20 divided by 18 is, I guess, 10 divided by 9, or if you stick it in your calculator, you get 1.11111. Okay, so 1.111 is where the second derivative is 0. And again, the intermediate value theorem tells us if we look anywhere else, it's not going to be 0. So all positive or all negative as you go to one side or the other of that 0 until you hit another 0 or where it doesn't exist. And there are no other zeros for this one, so that's it. This is just a line, 18x minus 20. So for bigger x's, I'm going to get positive. For smaller x's, I'm going to get negative. Okay, or you can stick in a number and check that. And the same thing with this one. This is a quadratic. So use your quadratic formula to solve this. The 9x squared minus 20x plus 7 equals 0. That'll tell you what the x's are. And you stick that in your calculator, your minus b, so 20 minus square root of b squared minus 4 times a times c, all divided by 2a. So that's the whole quadratic formula, a big mess. And you're going to get out 2 different numbers. And the numbers you get, according to the book, let's see, I didn't bother to do it, are 0.435 and and 1.784. So at 0.4, then there's this 1.11, then there's 1.787 maybe. Okay, and so these are where the first derivative is 0, is where a quadratic equation equal to 0, and stuck in the quadratic formula, found these two numbers. And so now I need to know, is it positive or negative between the two? Is it positive or negative afterwards? Is it positive and negative afterwards? So stick in a number at each of those three places. You could stick in 0 on this interval, you could stick in 1 in this interval, and you could put in 2 in this interval. Or you can just look at this and see that this is a quadratic formula. And so that quadratic formula represents a parabola, and it's opening up. So it had to be positive, then negative, then positive. Okay, so that's it. Now that I know those things, I'm just going to plug in the different values of x that we care about, these x's that we found, and calculate f of x. And then that will tell me how to graph my function. So that's it. We're just going to stick in these three values and figure out what they're going to be. So we have to put in 0.435. We have to stick in 1.11. And you're going to have to stick in 1.787. And by sticking in those values, we're going to figure out the important places on the graph. So these important places where the derivative is 0 are where possible places where I have a max or a min. In this case, I'm going to get a max. The first derivative test says that it's increasing here, then it's flat. Decreasing means that it must be where a max occurs, a relative max. And this one's decreasing, then 0, then increasing, means that 1.78 has to be a min, at least a local min. And so if I stick in this value to get out f of 4.435, I'll find out what is the maximum, the local max. What is the local or relative min at this spot? And then this place is where I switch between, this is where the second derivative is 0. This place is where I switch between negative second derivative, means this is concave down, to a positive second derivative where it's concave up. So this place is an inflection point. Okay, that's it. These are the important places. If we graph them, graph where they are, then most everything else will fill out. Another good trying to find where the x-intercept is going to be and where the y-intercept is going to be. Y-intercept is easy to check. We just stick in x equals 0, we get 0, 0, 0, 5. Okay, so I know that it's going to go through 5. But that 5 point is not anything special. It's not one of the maxes or mins or inflection points. In fact, it's where the first derivative is positive, going at that spot. And then it's going to keep going. It's going to be increasing, increasing, increasing until I get to 0.435. When I get to there, and then it's decreasing after that. So decreasing until I get to 1.787. So it goes down, and then it's going to go flat, and at 1.87 it goes positive again, so it's increasing. Okay, this is a bad graph, but it has some of the basics, right? Which is it's increasing here, decreasing, then increasing. Now, it would be a better graph if I found out what is that value. I plugged in 0.435, and this value is, and I plugged that in, and got those correct. And the next thing that would be good is if I found the inflection point here at 1.11 is, let's see, that's 7 or about 0.7 higher to 0.6. So yeah, it's about over here. So right here, I should actually have an inflection point. And I'm not seeing an inflection point here. I haven't graphed it properly. So I want to use a different marker to get it right. and make it concave down, concave up. And now this is a little better graph that I've drawn the curves and got the concavity correct. Now that's almost the only thing I'd look for. I want the 0.5 right, but I want to know what's that value and what's this value. So you need to stick these in to the original function, 0.435, get this one right, get this one right, and then that leads to A plus graph. Okay, I have no complaints after you've gotten this right, and you've gotten the concavity right, and you've got the first part right, which is the increasing and decreasing. Okay, so that's it. Now you just do that with lots of different functions, and that's for your homework on that section. So any questions about curve sketching?
Better to just, for the first derivative, if it's a quadratic form, to just jump straight to the quadratic formula rather than try and find the zeros?
So the quadratic formula tells you the zeros when you can't factor it by hand. So if I could factor it, I would have. But I looked at this and I see a 9 and a 7. The combinations here, I got 1, 3, or 9, and then a 1 and a 7, and those combinations won't make 20. So I look at that and I say, yeah, I can't factor this thing. So because I can't factor it, well, that doesn't mean there aren't any zeros. There are always roots of polynomials, though they might be imaginary. So the good news is no matter what quadratic you have, there's a formula that just instantly gives you the answer. Whether you can factor it or if you can't factor it, the correct formula gives you those correct answers, the zeros. Quadratic formula is better in a sense. It's more universal. It always works, but it's a mess. And usually it's more efficient to just look at it when you're in a math class and just factor it out. Because in a math class, we always fake it. We typically give you an easier one that can be factored than these ones. So this is just practice in the real world. Most real world problems, even when they're integers, can't be factored by hand with this. You need to use square roots and that sort of thing. And so the quadratic formula will always work.
Okay, thank you.
Yep. And so, I mean, typically if this was a fourth order polynomial, or a fifth or a tenth or e to the x or sine or anything else, then this won't be a quadratic when I differentiate it. And then if it's a cubic, if it was a fourth order and it becomes a cubic here, then you can't use the quadratic formula either. It turns out there is a cubic formula that we never memorize because it takes about a half a page to write down that formula. And there's a quartic formula, even if there's fourth order polynomials, and that one takes a whole page to write down the formula. It's gigantic. But then that's it. So you need to use numerical methods after that. Fifth order formulas and sixth order formulas, there are no universal formulas. But you can still always ask whether this real function is equal to 0 anywhere. And there's numerical methods that you learn, again, in Math 420, numerical analysis, for how to find the roots of any function whatsoever. And so engineers don't worry about it. They're like, stick it in a computer will tell you where the zeros are. Mathematicians are all about like, can I figure this out in my head? And they worry about it all the time. They're weird. Okay. So any other questions before we jump to L'Hopital's rule? So L'Hopital's rule is actually quite easy. You had a long hard time with limits before because we were doing all by hand, but now L'Hopital's rule is this pretty universal way that I don't know many other techniques besides L'Hopital's rule after being a lifetime mathematician for solving limits. So L'Hopital's rule is the way you can solve all the limits, and it makes it very, very easy. So L'Hopital's rule is the following. that when you're trying to find the limit as x goes to 0 of f of x or g of x, when these are both going to 0 over 0, then what you can do is take the derivative of the top one and take the derivative of the bottom. And if that is easier to do, then that's the answer. So that's L'Hopital's rule. I put a little star over here because it requires that a couple of things. First of all, it requires that f of x goes to 0 and g of x goes to 0 as x goes to 0. If you have 0 over 0 form, then you can take the derivative of the top, take the derivative of the bottom, and if that's simpler and you can see what that one is, then that's the right answer. So this is this L'Hopital's magic rule, and that's why I use a star here, is that I can transform this problem into an easier problem often. So let's do an example quick. So example 1 in section 6.7, they have 4 different pieces here, and I'll do all 4 of them. And so here's one where we're familiar. Limit as x goes to 0 of sine of x over x. Now you should already know what this one's answer is. It's just 1. Okay, we memorized that it's going to be 1 is the answer. But we actually used a pretty complex to do it. We did the trigonometry geometry of looking at the unit circle in order to figure that whole thing out. But with L'Hopital's rule, I can just check that, okay, limit as x goes to 0, I have sine of 0 is 0, so that's the 0, and on the bottom as x goes to 0, it's 0 over 0. So it's 0 over 0 form. So I can have this piece. I can use L'Hopital now. I can instead look at the derivative of the top and the derivative of the bottom, and that's going to be the same value if this one has a solution. So the derivative of the sine of x, cosine of x, I just take the derivative of the top, and then I take the derivative of the bottom. I put a 1 there. And now that limit is way easier than this limit right here. Because the limit as x goes to 0, cosine of 0 is 1. So it's 1 divided by 1. So that's it. So L'Hopital's rule, in many, many cases, makes things just everything a lot easier. Now, I want to put a bunch of warnings on this. We saved L'Hopital's rule till now, just so that you didn't get confused about the quotient rule, for instance. So this is not the quotient rule. I did not take the derivative of f of x divided by g of x. If I did, it'd be bottom times the derivative of the top minus top times the derivative of the bottom squared. I'm not doing that. I'm just differentiating the top and differentiating the bottom. And so sometimes students get confused and think, oh, that's how I differentiate fractions. So we push this rule way away from the quotient rule, just so that you practice the quotient rule over and over and over again, and you know this is not what we're doing right here. It's not the same process. The idea is that if a function is going down to 0 and this other function is going down to 0, if these two functions are both going down to 0, the question is what's the rate that this one goes and this one goes? Well, it turns out the ratio of how fast this one goes to this one go is the same as the ratio of how fast their derivatives go to 0. How fast the derivatives go down. Okay, anyway, there's a big long proof for that, and that's not long. It uses the mean value theorem, and again, that's a better proof for Math 301 than Calc 1. So this is our magic theorem. Let's try another one. Well, it's actually example 1, part 2 again. 1b, I guess. Limit as x goes to 0 of x squared over 1 minus the cosine of x. Okay, so we're going to do the exact same thing. As x goes to 0, I check the 0 over 0 form. I check that as x goes to 0, the top goes to 0. Sure enough, 0 squared. And the bottom, as x goes to 0, cosine of x, cosine of 0 is 1. And so I have 1 minus 1, so I have 0 on the bottom also. So it's the 0 over 0 form. So I can use my L'Hopital's rule. I'll give this a shot. I put a little star here to indicate that I'm using L'Hopital's rule instead of some other quotient rule or something. But there's another reason I put it up there. So I'll let that cliffhanger be there for a moment. So I check limit as x goes to 0 of this thing is Well, same as the derivative of the top is 2x. The derivative of the bottom, derivative of the cosine is minus sine, derivative of 1 is 0, and so this just cancels to positive sine of x. Okay, so now I've taken this function and turned it into a lot easier function to look at as x goes to 0. And I can just look at this and see the answer is going to be 2, because x divided by the sine of x goes to the opposite of sine of x divided by x, the multiplicative inverse here. It's just still 1. So this is the whole answer is going to be 2. Well, but that's not very satisfying. If you didn't see that, I can actually use L'Hopital's rule again. This is still, as x goes to 0, 2 times 0 over sine of 0 is 0. So I still have the 0 over 0 form. So I have this problem, and I don't know the answer to it, so I can ask, well, what if I use L'Hopital's rule on it? And the answer is 2 on the top. And if I differentiate 2x, I just get 2. And if I differentiate sine of x, I just get cosine of x. So we have now an even easier solution here. And as x goes to 0, the top goes to 2, and the bottom goes to 1. So this goes to 2 divided by 1. So that's what this one goes to. L'Hopital's rule says that that's what this one goes to. And L'Hopital's rule also says that this one goes to the same as this one if this one's solution exists. Okay, now that's partly, so that's our answer. This original one goes to 2. As x gets closer and closer to 0, this 0 divided by 0 looking thing is getting closer and closer to 2 as the x approaches 0. So that's our answer. One part of the reason that I use this star here is just to remind myself that I got to check the 0 over 0 form. Notice we just took the derivative, and we found something easy enough that I could check. What if I took the derivative one more time right here? What if I use L'Hopital's rule and take the limit as x approaches 0 of the derivative of the top and the derivative of the bottom? I get the derivative of 2 is 0. Derivative of cosine of x is minus sine of x. And as x goes to 0, well, 0 divided by sine of x is 0. So that's just what it is, even though it's going to 0 divided by 0. This one already is 0 divided by something that's not 0 when x is not 0. So we get the limit using L'Hopital's rule. This one is 0. Okay, we just showed that it was 2. And now I'm doing some weird crap to say that it's 0. What's happening is that I didn't use L'Hopital's rule properly. I have to check that it's the 0 over 0 form, or else L'Hopital's rule won't work. In this case, when I was looking at this one, this is not, as x goes to 0, I don't get the 0 over 0 form. As x goes to 0, the bottom, not 0. As the x goes to 0, the bottom goes to cosine of 0, which is 1. So not in the 0 over 0 form. So I am not supposed to use L'Hopital's rule on that. So if you don't use it properly, you'll get the wrong answer. Okay, so you have to be careful about that one little fact right there, to check that it's really of the 0 over 0 form. Okay, any questions about that? If not, then I'm going to jump ahead. There's a couple more in that example, but you can check them by yourself. So L'Hopital's rule, the point is it makes everything a lot easier, and it is the best rule on taking derivatives, no matter how complex the situation is. In Calc 3, you'll be doing limits with several variables, x's, y's, and z's, where the x's, y's, and z's all go to 0 at different rates or at the same rate, that sort of thing. And still, it all breaks down into this simple rule is the most valuable tool there. So L'Hopital's rule makes life easier. Well, then mathematicians make life harder, because if this is easy, well, then we're going to ask harder and harder problems until it's not easy anymore. So welcome to more pain. We're going to actually start looking at more complex problems, like, so this helps us answer L'Hopital's is good for can apply for 0/0 form. That's what we can handle. We can also apply to infinity over infinity form. So that's one more thing we can do. And so you can apply it to this one or this one. Now you can't apply it to a 2/1 form, right? Otherwise, remember that you'll get in trouble. So these are the only two times when you can do it. So let's do an example where we use L'Hopital's when it goes to infinity divided by infinity. And so let's see, example 2. And we have the limit as x goes to infinity of 3x squared minus 100x plus 2, all divided by 4x squared plus 5x minus 1,000. Okay, so now as x goes to infinity, we need to just check that we have the form, well, generally it's going to be infinity over infinity. So as x goes to infinity, I have x squared is going to beat out x, or 2, and so the x squared is going to win, and you're going to go to positive infinity in this case. So it's infinity divided by as x goes to infinity. The x squared here again beats out these guys. So again, I have infinity over infinity. So infinity over infinity form, I'm ready to use L'Hopital's rule. So what I do is differentiate the top, differentiate the bottom, and we're ready to go. And I just get 6x minus 100 is the derivative of this quadratic. On the bottom, I get 8x plus 5. Okay, great. That is a lot easier than that. At least looks better. But again, as x goes to infinity, I have the form infinity divided by infinity. So I use L'Hopital's rule there after checking it. Now I check that it is really of the form infinity over infinity, so I can use L'Hopital's again. As x goes to infinity, I'm going to get, well, derivative of this top is 6, and derivative of the bottom is 8. And then the limit as x goes to infinity of 6/8 is 6/8. That's our answer. And that's correct. And we could have checked this, by the way. You should be able to look at this one from the beginning and just see that's the answer. Remember, we've done problems like this before. As x goes to infinity, you just look for the highest power of x and divide everything by that highest power of x, and then check them term by term. And so this one would, you just look at the leading coefficients of the x squared and x squared. They're the highest one. So 3/4 is actually the solution that I would have got. Well, it's 6. No. You just divide, factor this out. You have there's a 2 in top and bottom, and so they're the same thing. Okay, so that's a better answer. I'm taking a half point off of this one for not simplifying. Okay, any questions about that? Okay, well, it's gonna get trickier. The question now is, what other sorts of really complex limits can we handle? And it turns out a lot of them. So we did infinity divided by infinity. We did 0 divided by 0 work. So L'Hopital's is good for that. But what happens when I get a form that looks like 0 times infinity? So I just want to talk right now generally about these indeterminate forms. So whenever I get infinity divided by infinity, I don't know what the answer is going to be. It could be anything. It could be infinity, it could be 0, it could be 782. In fact, last time we got the answer was 3/4 for infinity divided by infinity. So it's an indeterminate form. We haven't determined what it is. It's a form that's ambiguous. We don't know what it's going to be. And so same thing with 0/0. Well, same thing with 0 times infinity. 0 times anything is 0. Okay, so no, this should be 0. Well, no, infinity times anything is infinity. So actually, if you get something vanishingly small times something greatly large, it depends on how large this is and how fast it's going to infinity versus how small and how fast it's going to 0. So if this is going to 0 really fast and this is slowly growing to infinity, this wins, and this would be 0. Or if this is going to infinity really fast and this is going to 0 slow, then the answer is infinity. So this is indeterminate form, just like these. The answer could be anything. And the same thing happens if I get infinity minus infinity and a few others. Determinate forms, though, some things we do know what they are. Like if I have infinity plus infinity, there's no ambiguity there. If I have a gigantic thing plus another gigantic thing, I get a gigantic thing, okay? And so something going to infinity plus something going to infinity is something still to infinity. So that's determinate. I know what it's going to be. The answer is infinity. Another form that would work, infinity times infinity. Okay, a big thing times a big thing is a big thing. There's no ambiguity there. Oh, yeah. Thank you. There's no ambiguity here. We're going to always know the answer is infinity. That's a definite answer. What about, okay, where do I put infinity to the infinite power? Well, it's also infinity. Okay, this is also a determinate form. And there's a few others like, let's see, 1 to the 0 power is always 1. What about 0 to the 0 power? 0 to the 0 power is always, well, 0 to anything is 0, but anything to the 0 power is actually 1. So it turns out, no, that's not a determinate form. That's an indeterminate form. Okay, depending on how fast the exponent goes to 0 and how fast the base here goes to 0, it could turn out to be anything. Okay, so we leave that as indeterminate form. Another indeterminate form, infinity to the 0 power. If this is going to 0 and this is going to infinity, is it going to be 1 or is it going to be infinity? Well, it could be anything. Again, that's the point. And finally, there were one is the infinite power. See, if it's like 1.1 to the infinite power, that's infinity. So if this is going close to 1 slowly, and this is going to infinity fast, then the answer is infinity. But it could be that I was going to 1 really fast and going to infinity real slow, so that this goes to 1. So it could be anywhere between 1 and infinity in 1 to the infinite power. So all these are indeterminate forms, and we don't know the answer. Okay, let's get into some actual examples here. But I guess there's a couple left here that I didn't do. 0 to the infinite power, that's always just 0. Okay, 0 to the 1 power, that's always just 0. Okay, so there's certain combinations that are clear, and there's certain combinations that are not clear what the answer is going to be. And let's do an example. I don't have them ready here. I could make them up, but I think I just want to copy from the book as much as I can. Follow along so you can follow along later. Oh, and it's going to be a little difficult. I have to get to section 6.8, 6.7. So any questions while I'm searching through the book here to try to find 6.7? I'm not going too fast on anything, am I?
Nope.
Great. Okay, 6.7. And Okay, so example 3 here. It's the next thing we're on. So as promised, now they're getting trickier. Okay, so these indeterminate forms that are weird require some extra algebra or extra thinking. To give them a solution out of them. Limit as x goes to 0 from the right is example 6.7.3. So I'm on page 335. Okay, and the first example is x times e to the 1 over x. Now I'm taking it as x goes to 0, and they were careful to say only on the right. Okay, the problem left is that I can't take. Well, anyway, let's not get into that right this second. I'm taking it as x goes to 0 from the right. So what is, out of curiosity, the limit as x goes to 0 from the right of just the 1 over x? See, just the piece up here, I want to know as x goes to 0, what's that going to? As x gets closer and closer to 0, I'm dividing 1 divided by a tiny fraction, like 1 divided by 1/1000th, and 1 divided by a small number is a big number. So from the right, for positive numbers, this is going to be positive infinity. Okay, so as x goes to 0 from the right, this part is going to positive infinity. So e to the positive infinity is still infinity. So this thing is going to be infinity, and then times as x goes to 0 from the right times 0. Okay, and infinity times 0 is always equal to 0. Or no, maybe infinity. Well, no, the whole point is it's indeterminate. That's not right. It's unknown. So we don't know what the solution is, even though I know this is getting infinitely large and this is getting infinitely small, approaching 0. The combination, I don't know which one's winning. Is this going big faster than this one's going small? I don't know. Okay, well, I do know I've seen this problem before, but we're going to solve it right now by using L'Hopital on this. But we can't use L'Hopital on it right now. It's just 0 times infinity. Remember, L'Hopital is only for infinity divided by infinity or 0 divided by 0. So the trick on all these 0 times infinities is to rewrite it. Rewrite 0 times infinity as, well, either way, but I'm going to do in this one, leave the infinity up here and do 1 divided by 0 down here. So 0 is the same as 0 divided by 1 divided by 0. So I just do 1 divided by that. In other words, I have infinity over infinity. So 0 times infinity can be rewritten algebraically, so it's ready for L'Hopital's rule. So what do I mean? So this is just a side thinking. What I mean is I'm going to take this down here and leave the thing that's getting infinitely large on top and put the x in the bottom. 1 divided by 1 divided by x is the same as x. Like so. So that's going to work now. So now as x goes to 0, this problem is going to be easier to handle because I'll be able to use L'Hopital's rule on it. So with that trick of switching 0 times infinity to infinity divided by infinity by putting 1 divided by 0 on the bottom, we can now just take the limit of the derivatives of the top and the derivative of the bottom. Okay, and well, it doesn't look like we've made it easier, but at least we can now use L'Hopital's rule on it. So I use L'Hopital's rule on e to the 1 over x, and the derivative of e to anything is e to that same thing times the derivative of 1 over x. Remember, that's x to the minus 1. It's minus 1 over x squared when I differentiate it. And derivative of 1 over x is minus 1 over x squared. It's the same top and bottom, this one. So algebraically, I can cancel those before x goes to 0. And now as x approaches 0, this is the same as this. So we have the limit as x goes to 0 from the right of e to the 1 over x. And this one we already checked at the beginning. Remember, it's going to infinity. That's the infinity form. The 1 divided by x is going to infinity as x vanishes to 0. As x gets small, this gets big. And then e to a big is still big. And so that's the answer to our problem. Okay, that's a tricky one. Okay, and then there's a couple other forms that they're going to do. So on number 3, so example 3, part 3, the next one is going to be limit as x goes to infinity of the natural log of x plus 1 minus the natural log of x. Okay, so as x gets larger and larger and larger, I have the natural log of something larger and larger and larger, minus the natural log of larger and larger and larger. Well, you have to know what the graph of the natural log looks like and know that it actually shoots off to infinity as x goes off to infinity if you want to solve this problem. So this is of the form infinity minus infinity. Okay, and now which one's bigger? Well, this one's bigger. So it's infinity minus infinity. Well, how much bigger is this one than this one? As x gets really larger and larger, how much bigger is it? Well, it turns out as x gets larger and larger and larger, natural log of x grows slower and slower and slower. So it turns out this is going to be not much bigger than this. And so the answer is going to be 0 in this. But we weren't sure if this is a lot bigger than this one. It could have been anything. So I'm not sure it's 0, except for the fact that I've seen this problem before, and I am intimate friends with the natural log function. Okay, we know each other really well. I've spent many years studying this function, and so that's why I know that it's going to be 0. But how do you know? Well, we need to not do any of that thinking. We need to use some sort of L'Hopital's rule on this. And I can't use L'Hopital's rule on infinity minus infinity. I have to have infinity divided by infinity or 0 divided by 0. So I have to do some algebra to change it around. The same as we did on this last problem that had 0 times infinity. I have to algebraically play around with it until I get of the form infinity over infinity or 0 over 0. So on this problem, as x goes to infinity, I have infinity minus infinity. What am I going to do? Well, the natural log function has a property that when you add two functions, two logs, I can just take one log and multiply the two pieces. When you subtract them, I just divide this one divided by this one. So that's the same function as x plus 1 divided by x. So as x goes to infinity, the natural log of x plus 1 divided by x is a lot easier to handle. In fact, ignore the natural log for a moment and use the property of continuity of log. I can take the limit as x goes to infinity inside the log. So it turns out that as x goes to infinity, I have this divided by this. And this is infinity over infinity form. So inside of there, I can actually use L'Hopital's rule. And then the answer is going to be natural log of the derivative of this one, which is 1, divided by the derivative of that one, which is 1. So either use L'Hopital's rule on it, or also remember, we know how to handle these rational functions. It's just power 1 are the biggest pieces. And so the coefficients in front of them are going to be what matters. So the answer is the natural log of 1. Okay, and I'm taking a half point off for that answer because you should know what the natural log of 1 is. It's 0. As x goes to 1, natural log of 1 is 0, just like e to the 1. E to the 0 is 1, natural log of 1 is 0. Okay. So that's that one. And so there's a few other ones that are even more complex. Let's do the next example. When we handle things like 0 to the 0 power, 1 to the infinity, or different pieces. So last example for the day is example 4 here. So example 4. We're going to take the limit as x goes to infinity of 1 plus 1 over x to the x power. So this is of the form as x goes to infinity, 1 over x goes to 0. And so I just have the form 1 plus 0 is 1, all to the infinity power. Okay, and 1 to the infinity is 1. No. 1 to the infinity is infinity. No, okay. 1 to the infinity could be anything. It's another indeterminate form. So that's not a good answer. Okay, it's just this form. So it's not equal to that, it's of that form. And so I need to do something else whenever we have that situation. I'd like to use L'Hopital's rule. I'd always want to use L'Hopital's rule. Unless it's super simple and I can just see the answer. I want to use L'Hopital's rule. And so in order to do this, I have to do some algebra to get it in the form infinity over infinity or 0 over 0. So algebra to get this thing down, well, when I have a power, then always the solution is I want to take the log of it to bring the power down. Okay, so that's my trick. And so what I want to do is take the limit as x goes to infinity of e to the natural log of this whole thing. E to the natural log is like it isn't even there. It's like I'm adding a 5 to the top and bottom of a fraction. I can always do something to the top and bottom of a fraction. Well, I can always take a function and its inverse to something, and I haven't changed it. So it's e to the natural log of 1 plus 1 over x all to the x power. And the reason I do that is because I take the natural log of something to a power, I can bring this down in front of the natural log. Okay, I'm sort of ignoring the e for a moment and just pretending I'm only on this line. And so I can bring the x down to that part of the line. So this is the limit as x goes to infinity of e to the x times the natural log of 1 plus 1 over x. Just keeping the e along. And again, I just have this line all in the top. So that's a little bit better. Well, it doesn't look better at all to me. Like I had this nice cute form, and now I've got e's and natural logs, all this sort of thing. Well, what I've done is I've taken the infinity down, and I have the natural log of the 1. So I have infinity times natural log of 1 is infinity times 0. So I have e to the infinity times 0 form. And we already showed what we do when we have infinity times 0 or 0 times infinity is I put the 0 in the bottom or I put the infinity in the bottom. This time I'm going to put the infinity in the bottom. So when I have infinity times 0, I can put the infinity in the bottom by doing 1 divided by infinity times 0. So I'm just going to take the x and I'm going to put it down here as 1 divided by x. It's the same as x is the same as 1 divided by 1 divided by x. Infinity is the same as 1 divided by 1 divided by infinity. And the reason I do that is because 1 divided by infinity is just 0. So this is the form 0 divided by 0. And this I can use L'Hopital's rule on. Okay, so that's our game plan. Is that we saw this mess up here. First thing we're going to do is try to bring the x down with the natural log. So we do that. We bring the x down with the natural log. Now I have infinity times 0. So I'm going to put the infinity in the bottom now. By taking e to the, okay, so it's e to all this stuff, x times the natural log of 1 plus x, 1 plus 1 over x. And then this x gets sent down to the bottom as 1 divided by x. Okay. Okay, and we're in the same situation we were before. I have a 1 over x and I have a 1 over x here. So now if I do L'Hopital's rule, I'm going to take derivative of the top and derivative of the bottom, and the 1 over x and 1 over x's derivatives will cancel each other. And so this is going to work out. So I'm now going to take limit as x goes to infinity of e to the power of, I have to differentiate the top and differentiate the bottom. And boy, I'm not going to fit it in that little tiny spot. So I'm going to have to do an extra line here. Okay, so the derivative of the natural log of 1 plus 1 over x. So again, I wasn't trying to be mean on problem number 2 in the midterm when I was doing really complex questions, right, of how to take the derivatives of things. These things pop up all the time in natural problems. So what do we get? Limit as x goes to infinity of e to 1 divided by, so the derivative of the natural log is 1 divided by 1 plus 1 over x times the derivative of 1 over x. Okay, and we know what that one is. We did it just earlier. It's negative 1 over x squared. Okay, that's the derivative of the top. And I also have to do derivative of the bottom. Well, it's the derivative of 1 over x. And I don't want to say it's minus 1 over x squared because I have it written like there. So these guys will just cancel and have this. Now I have the limit as x goes to infinity of e to the 1 over 1 plus 1 over x. And this one is now easy to solve. So this is our form that the L'Hopital one time made everything work out, made something easier to handle, turned it into something clear, because as x goes to infinity, 1 over x goes to 0. And so this is just e to the 1 divided by 1 plus 0. So the answer is e to the 1. 2.718, ... So e is the solution to this e to the natural log of all this stuff. They were canceled. So e is the answer to all this stuff up here. It's just 2.718. So this solution of 1 to the infinity wasn't infinity, it wasn't 1. Turns out it's 2.7 and a little bit more. So I'm pausing here to concentrate on this because this is an incredibly valuable formula. So from one perspective, from the mathematician's perspective, here's one way we can get at e. E is the number that you get when you put 1 plus 1 divided by big number, 1 divided by 1,000,000. I take it to the million power. Then e is approximately that. That's one way I can find out what e is. Okay, that's not how they do it. There's a better algorithm for finding e faster, but that is one way to think about it. The reason it's actually useful is because this is basically the compound interest formula. So you will see this formula again and again in all applications of mathematics. And the reason is because compound interest is how the world works. Compound interest is how your bank statement works, of course. If you put in money, then you're going to get a percentage of your money, and you keep repeating that over and over. It works with growth of population. So bunnies grow with exponential growth with this same sort of thing, that each time you add a new bunny, and then you repeat over and over again. So you will see this formula again. We're not explaining it carefully right now, but I'm just warning you, this is a fundamental function, fundamental formula, and E is a most important number in mathematics. And so the fact that you have this representation for it is one of the reasons the function is actually, sorry, the number is actually interesting. Okay, so that's the big trick there, is taking 1 to the power of infinity and taking the exponent down by doing the e to the natural log. Are there any questions at all about that?
There's one in the chat.
Oh, one in the chat? Let's see. Why can't we use 10 to the log base 10? Oh, there's nothing wrong with using 10 to the log base 10. If you use 10 to the log base 10, then that works fine. And log base 10 has that property that I can bring the x down. So there's nothing wrong with that. Base 10, then when we get to here, and we're going to use L'Hopital's rule, then it's all the same. I just have a 10 here instead of an ugly little e that we're all afraid of. And the log base 10 we're a little more comfortable with. The problem is, as I use L'Hopital's rule, when I differentiate the log base 10, then I'd get an extra constant. And the extra constant when I differentiate log base 10 is basically, well, the natural log of 10. So it doesn't actually simplify anything for us. If we get comfortable with using exponential function with e as its base instead of 10, then the calculus is faster and easier. And that's the main reason we use e. It's just these calculations are easier. So if we used log base 10, you get the same answer. You'd still get everything to work out. It's just that you'd have this extra 10 to the log base 10 of e, right? And 10 to the log base 10 of e would give you e. You'd still get e as the answer. It's always the same. There's only one answer to a math question that has a number limit. Otherwise, the math doesn't mean anything. So you'd always get the same thing. But if you use log base 10 instead of natural log, you just have this extra step. And so that's why mathematicians, engineers, scientists of all stripe get comfortable with using the base e. It's the natural logarithm instead of the base 10 logarithm is for us monkey people who have 10 digits, okay, with our hands. And so we're more comfortable with base 10 thinking. Computers are more comfortable with base 2 thinking. So why not use base 2? Well, again, because if I use base 2, I'd still get this natural log of 2 extra function in here, extra coefficient. And so the step would be longer. So mathematicians use this so often that we are going to use just one base, the base e, and that's the one that's just a little bit more efficient. They didn't always use it. It's e is after Euler's number. So, and Euler was in the 1700s, and the inventors of calculus were like the late 1500s before Newton and Leibniz. And so e was not recognized always as the best, most efficient way to do things. But by the time Euler came around, he used it to great effect. Okay, any other questions before we break for the day, for the week, really? Okay, well, I'm gonna drop out of YouTube then.